Good afternoon, everyone. I'm Yogi Joshi, and I'm one of the members of the Real-Time Embedded Software Group at the University of Waterloo. And today, I will be providing you a demo of one of the tools which we have been developing at our labs. The tool is Runtime time-triggered heterogeneous monitoring tool, which takes a C program and a set of LTL properties as input, and it produces an instrumented C program as an output. The instrumented C program can be monitored at runtime. So in this example, we'll consider a monitor with fixed polling period. So as the input to the tool, we need to provide a C program. So let's first consider a simple C program. So this is the program which we will feed as an input to the tool. The program generates Fibonacci series, and we have a number of variables which we may want to monitor. So consider a variable I. The variable I is used as a loop counter. In this loop, the variable n has an initial value of 30, and it's used to have a cap on the length of the Fibonacci series. Further, we have two variables fnew and fold, which generate the values in the Fibonacci series. So let's consider monitoring these four variables. So we have a property file which has the LTL properties. So let's consider properties one by one. The first property is that the predicate A should be eventually true. So the predicate A states that the value of variable I should be greater than 10. So in the program we can see that I is less than or equal to n in this loop, and it's incremented, and n has a value 30, so I would eventually become greater than 10. So this property would hold true. The next property is that the predicate B should always hold true. So the predicate B is I should be less than or equal to n. In the program we can see that I would become greater than n once the loop is terminated. So this property would be violated. Third property is that the predicate C should always hold true. So predicate C states that the value of variable fnew should be greater than the variable fold. So in the program we can see that the value of variable fnew would usually be greater than fold, but here we have a declaration which doesn't have any initializers. So we can see whether this property is satisfied when we run the tool. So let's provide input to the tool. We need to provide here the directory where the source code is there. So let's provide the directory where we have our Fibonacci series source code. Next is the output directory. Here the instrumented source code would be placed by the tool. So I'll create a directory and we'll have our instrumented code in this directory. Next is the property file path. So we have a file called pbo.cfg in our input directory. After this there is a configuration part. So we'll have a monitor with fixed polling period. We'll use the algorithm which is sequential, so that means the program history trace, the values of the critical variables would be processed on a CPU in a sequential manner. Next is the invocation type. So this is synchronous, that means the monitor would be blocking, it would block the running main program. Further we have target polling period. So this is the frequency with which the monitor would be invoked, and we want to have it as 19 cycles. Further we have the buffer size, which is used to hold a history of the values of critical variables. So we'll have buffer size as 1000. Now we have the method which we want to use for generating optimized instrumentation. So we'll use ILP solvers for optimized instrumentation. Now we have this flag log trace, which means that we can have the running program log its values to a particular file. So this would allow us to check the values and their changes in the program at particular instruction. So we'll enable this flag and now we'll run the tool. So the tool shows that the monitor generation is successful. So now we'll go to the directory and check the instrumented code. We'll compile and run the instrumented code. So now I'll compile the instrumented code here and I'll run that. So the instrumented code is run, and now we'll be able to see the output log of the instrumented code. So as we had enabled the trace, we'll have a back trace which will show us the changes to values of various variables, and it will also show whether a particular property was satisfied or violated. So let's see the trace. So here in the end we can see that the property 0 is satisfied. This was the property which stated that I should eventually become greater than 10. So we can see that the trace shows a CSV output which has the line number and variable values. The line number suggests us that a particular value of a particular critical variable was changed at this particular line number. So we can see that the second column in the CSV file is the value of variable I, and we can see that value of I variable got incremented and it has become greater than 11, greater than 10 at the line number 25. So this means the property got satisfied at this point. The second property is I should be less than or equal to n, which is violated. Now in the end we can see that value of variable I is 31, but the value of the variable n is 30. So value of variable I got incremented to 31 at line number 25, so the property got violated. Third property states that f new variable should have a value greater than f old. So we can see that this column and this column has the value of variable f old and f new respectively. So f new is here greater than f old, but at the very beginning of the program we can see that both have values 0 and 0. So f new is not greater than f old at the beginning of the program. So this property is violated at that point. So by using this tool you can see the backtrace of the changes in the values of various critical variables, and we can determine the cause when a particular property is violated. In addition to that, we can see the result of property violation or conformance when the program is run. So this is about the fixed polling period monitor, and that's all I have for you. Thank you very much.